Hello, calculus. We are going to take some notes on section 114, connecting infinite limits and vertical asymptotes. And I will preface this by saying this section should feel really great because we did a lot of this before. And I know I keep saying that, but I just want to remind you that you are smart and you know this. So consider the following functions. We've got f of x is equal to 1 over x minus 1, and g of x is equal to 1 over 1 minus x quantity squared. So let's think, what do we remember about these? The first one I will say is, hopefully we know it's a rational function, and we see that it will have a vertical asymptote at x equals 1. So I'm going to add a vertical asymptote at x equals 1. And our horizontal asymptote, we haven't done this for a while. But if we think back, we're comparing degrees of the numerator and the denominator. Since the numerator has a lower degree than the denominator, it will have an asymptote at y equals 0. We will remind ourselves of both those rules in a little bit, but I know that my asymptotes are going to be at x equals 1 and y equals 0. And then if I want, I could plot some points, but I also feel like I've seen enough of these functions, so I can assume that it's going to look something like this. And for right now, sorry, that was kind of bad. You can just trust me. Then let's look at the second. Move this over just a little. There we go. All right, our second function is going to be very, very similar, right? It has that vertical asymptote at 1, and it has a horizontal asymptote at 0. But this one is slightly different, and maybe some of you remember this and maybe some of you don't, but this is a really important thing. Because of this multiplicity, remember the exponent, multiplicity of 2, if we remember our zeros, what happened when we had a multiplicity that was even is they bounced. So what happens with these graphs is we see both sides, oh, sorry, that was really bad. Both sides of this function are going to be on the positive side of the x-axis. So I just went through those really quick, and we're going to review that again later, but here are my graphs. So they want us to find each limit and confirm the result with the graphs above. Realistically, I'm going to use these graphs to find the limits. If you want to pause the video right now and try these problems on your own, I think that's a really good idea, but I'm kind of just going to go right into it. So the limit as x approaches 1 from the negative side of f of x, well, it's going down, so it's negative infinity, therefore does not exist. The limit as x approaches 1 from the positive side, my graph is approaching positive infinity, therefore does not exist. And the limit as x approaches 1, well, there's a vertical asymptote there, so that limit does not exist. Over on our g of x, the limit as x approaches 1 from the negative side is positive infinity, therefore does not exist. On the right side, the limit as x approaches 1 from the positive direction, it's also positive infinity, therefore does not exist. And even though both of these are approaching the same thing, we would still say that the limit as x approaches 1 of this function does not exist. Remember, because that's a vertical asymptote, that is one of our discontinuities. So the think about it question is kind of an, like, very, how do I say this? A very simple think about it. What do limits that produce results of infinity or negative infinity say about that function? So if we didn't have the graphs here, if we couldn't see those graphs, and we just knew this information, what would we know? Well, we would know that there is a vertical asymptote. Because my function is approaching either positive or negative infinity. Thus, it's, oops, that was a really bad asymptote, but it's going up towards that asymptote or down towards negative infinity. So vertical asymptotes. These are our good old friends from Honors Trig Pre-Calc. Technically, we have a definition of vertical asymptotes that is very calculus. So if the limit as x approaches some value c from the negative side of that function is equal to either positive or negative infinity, or the limit as x approaches c from the positive side of that function is equal to positive or negative infinity. If either of these things are true, then x equals c, that line, is a vertical asymptote. We just saw that on the last page, and hopefully that's not super shocking. If I'm approaching infinity, as I get close to that value c, so let's say this is c, that would mean I actually have an asymptote there because my function is approaching either positive or negative infinity there. So this next example says, determine all of the equations that represent vertical asymptotes for each of the given functions. What do we remember about finding vertical asymptotes? Well, we find them by finding the zeros of the denominator. So for this first one, I can't factor the top x squared plus 1, but the denominator is the difference of squares. So x squared plus 1 does not factor, but we have x plus 1, x minus 1. So that means our vertical asymptotes for this first one are x equals -1 and x equals +1. For our second function, we can factor both the top and the bottom. Our numerator is going to factor into, if you want to pause it to try it yourself, please do, but our numerator will factor into x plus 4, x minus 2, and our denominator, difference of squares, x plus 2, x minus 2. Ho-ho, what do we got here, guys? We have a whole, right? A removable discontinuity. But that still leaves us with one vertical asymptote at x equals -2. We have done this before. We did this last year, and we did this actually just recently when looking at wholes. So technically, what we just found out, even though we knew this, is how do we find vertical asymptotes? Remember, they are the zeros of the denominator. But of course, that's after we find any common factors, which are wholes, or again, removable discontinuities. Okay, well, kind of discontinuities. We have two more examples. Again, it's the same type of thing. Determine the vertical asymptotes for each of these. If you want, take a moment to pause the video and try them, but realistically, we have done this so many times in pre-calculus and already so far in calculus that I think you're probably okay. Finding the zeros of the denominator in this first one, well, that's just x equals 1 will be my vertical asymptote. F of x is equal to cotangent. Ooh, we have to think a little bit. Cotangent is the reciprocal of tangent, right? Or tangent is sine over cosine. That means cotangent is cosine over sine. All right, so now I need to find the places where sine is equal to 0. I'm going to consider the graph of sine for a moment. That's what I like to do, but you could think about the unit circle too, right? This is sine. And if we remember, it goes from 0 to 2 pi. That means this would be pi here. All right, so where is sine equal to 0? Sine is going to be equal to 0 at any multiple of pi. So I'm going to say my vertical asymptotes will be at x or theta equals pi n, just to say that it can be any multiple of pi. And my last example is another example where we're not going to use the graph. We're going to kind of think about it in terms of a table. So find each limit to the best of your ability without using a calculator. Hint, try making a table of values, allowing x to get closer to 1 on the appropriate side of 1. So for this first problem, the limit as x approaches 1 from the negative side. I am going to make a table of values like it suggested. We've got x and f of x, and we are approaching 1 from the negative side, meaning I am getting closer to 1, but I am smaller than 1. So I'm going to plug in 1/2 and then 1, actually, hold on. I'm not going to do 1/2 first. I'm going to do 1/4 and then 1/2 and then 3/4. So I'm going to plug these in. 1 over 1/4 minus 1 is really 1 over negative 3/4. The reciprocal would be negative 4/3. For this next one, I'm plugging in 1/2, so 1 over 1/2 minus 1 is 1 over negative 1/2, negative 2. And then we've got, sorry, my screen's not big enough, 3/4. So 1 over 3/4 minus 1 is 1 over negative 1/4 is negative 4. And now let's look at what's happening. As my x's are getting closer to 1, what is happening to these y values? They are progressively getting more negative, right? Getting more negative. Thus, I can say, because I know that there's an asymptote at 1, so I know it can't actually be something, I am getting more negative. What am I approaching? I'm approaching negative infinity, and of course, therefore, I do not exist. So this first limit for a is negative infinity, therefore does not exist. I'm going to let you try the other table and see if you can figure out the limit as I approach 1 from the positive side. And that is it for our notes for today. I will see you in class tomorrow for the rest of Unit 1. Have a great Wednesday and take your quiz if you have not already. Good luck. I will see you tomorrow.